Okay, so very good morning to all. We are going to start session 7. So, this is the first session in day 3, and our resource person for this session is Mr. Karthik Kameswaran. So, since he is familiar to all of us, so I think he needs no fresh introduction. So, I request Mr. Karthik to please deliver the talk.
Thank you, sir.
Yeah.
Uh, I hope the screen is visible. Uh, so today we are going to briefly look at the quantum communication, the foundations of it, and the relation to quantum hardware. Uh, so as we all know that the communication is backbone of all computing today, and standalone computing, while we can do for whatever that we could. Uh, in absence of a communication or long distance communication, performing standalone computation alone is not going to help much. So we are going to look at quantum communication specifically because this branch has been around for quite some time, and quantum communication, in fact, they are probably the most advanced of all quantum technologies, and it's actually closest to the wide market adoption. If you look at the number of companies, the number of commercial products which are available in the market, you'd be surprised that there are about 7 to 8 companies which are actually offering quantum communication based product. So they do offer quantum key distribution, and that's going to be the focus of the talk today, because quantum key distribution is actually very important going forward, and it's well established. And when you start pairing up quantum key distribution, a secure quantum communication, and a reliable quantum computing together, you are essentially looking at an absolutely unbreakable network, and something which is, of course, it is fragile. It's not that it cannot break down, but per se you cannot there are no security vulnerability in terms of hacking into it. There are certain POCs that establish how certain level of hacking can be done into it. People have cracked, but then it's by and large it's very very secure as against our classical computing. So uh, the major focus here is to see if what are the different applications that come along with a quantum communication, quantum network, and the foundations of it. The other application which we see with quantum network is also in the precision clock. We know that atomic clocks are 1 billion year kind of precisions are already available. But what we are looking at is we are looking at a quantum network of clocks. And as we all know, clock is one of the most fundamental component for all electronic circuitry, major electronic circuitries, and thereby as an extension to the computers. And this has been in research implementations for past about 8 years now. So it's actually a pretty well evolving field in itself. So quantum communication, if we come back to the focus of quantum communication, we find that photon based quantum communication is a natural choice, and this is an extension of what we have as an existing infrastructure. The whole communication today is based on fiber optics, because it's fast, and the coaxials are already on their way out. So unless we are talking about a very very old setup, most of the places we do have of the fiber optic infrastructure, and this can be augmented for quantum communication. And quantum communication, while do not depend on fiber optic alone, there are obviously superconductors and other options also. But optics obviously are the most viable and efficient. One, speed of light. Two, there is a very well established infrastructure. Certain augmentation need to be done, but apart from that, it's already there. Uh, and also, if you look at the overall decoherence of the quantum state, it's much lower in optics than another option. When you have to talk about superconductors, you have to maintain a particular temperature, and you would have to ensure that the interference is minimum. So the risk of decoherence is much higher in superconductors, whereas in optics it's much lower. But if you, having said that, if existing optic infra cannot be just simply lift and shifted to use with quantum photons, because quantum photons obviously have certain properties of its own. And obviously, existing optic infra, if they are already carrying classical data, you cannot simply add uh, you know, uh, quantum photons to it and simply say that, oh, I can as well, I might be able to transfer. That's not going to happen, because obviously quantum photons are susceptible to interference, and the classical data can obviously distort the quantum photons. So obviously we're not going to use them in conjunction, but what we can do technically is be able to use that infrastructure, some of the infrastructure, the cable, of course, the certain nodes obviously will not be able to use the amplifiers from an existing network. But what we can definitely do is we can use the cabling and such stuff. Uh, it's not absolutely fully suited for a long distance communication, in the sense that you cannot have a straight fiber optic cable for like 10 kilometers and say that, oh, I have a 10-kilometer fiber optic cable and now I'm going to use it. That's not going to happen, because there are obviously real world losses, and real world loss with a classical data signal is much easier to control. And even if there is a loss of, let's say, about 40-50% of signal strength, we can still be able to recover with a very high fidelity. Definitely, some amount of errors will creep in, but that's more manageable. Whereas in case of quantum photons, if you are losing anything like 40-50%, definitely it's as good as it's as good as a dead communication, because you start looking at very high error rates, and there is no way to recover them. So if you recollect the quantum no cloning theory, we cannot obviously recover by classical methods of recovery. But then how do commercial quantum key distribution products exist? I mean, there must be some way. So they deploy something called as a quantum network. In fact, in this year, Chinese scientists had established, integrated quantum communication network. Where they combined like about 700 odd optical fibers on the ground, and they had two ground to satellite links. So with ground satellite link, they can obviously be able to transport it much better, because outer space is much less cluttered as against the ground communication. And they were able to achieve QKD over a distance of 4,600 kilometers. Now, which is essentially you're talking about across the whole country. So if you are able to do that, that's commercial deployment. I mean, it's no longer scientific or a research deployment. It's close to a commercial deployment, where you are able to achieve that kind of distance, and with a high degree of reliability. And QKD has not been very new. Rather, it has been fairly been around for almost 17-18 years now, in good research and commercial products. In fact, about 15-16 years ago, there was a financial transaction between two European countries. I do not recollect which of them, but there was a financial transaction which was done using QKD. So This is a fairly what you can say mature technology in the sense that it is out of the lab and it's there out in the commercial world. There's a company called QNU Labs. If you want to look up for QNU Labs in India, so this is if I get it right, it's probably Bangalore-based company, and they have been doing this quantum key distribution for quite a while now. So that's the current status of quantum communication, and we really know that uh, we we should be looking at quantum communication in conjunction with our quantum computing. uh, we would really want to explore how they pair up together. It's not just that you put classical data over quantum key distribution network and you say that we have done a quantum network per se. It's not a quantum network. For a quantum network to actually exist, we need the quantum processors to be available, the end nodes which are actually quantum computers. So they should be able to transmit and receive qubits. And we obviously have a physical layer. Physical layer, obviously, we know that we have various components like the medium which carries it, the repeaters, the error correction components, and especially in case of quantum network, we need something called as a quantum purification. We'll come to that later. Uh, so the basic structure, if you look at the quantum network, it's very similar to a classical network. If we talk about classical network, what we have the repeaters, we have the medium which is carrying the signal, we have the error correction components, and then we have the end computers which are actually performing this. So in a classical network also we have a similar one. In quantum network also we have similar setup. Uh, so the difference is obviously the quantum processor and the purification part of quantum computing. So these are the two variations, and it's fairly simple with QKD. Actually, we can use beam splitters and photo detectors, and we can establish QKD. But for other use cases, you cannot just have a beam splitter and photo detector, because you need an elaborate set of communication components. You need to be able to transfer reliably, because we spoke yesterday about when we are talking about superconductor transmon qubit, we spoke that the output temperature, output voltage is usually in microvolts. Now that needs to be converted to a stable signal. You cannot have a microvolt level signal being able to power communication for kilometers. So that definitely is not going to happen. Even for few meters it cannot sustain, so we will be having a lot of loss. So obviously we'll look at, and the other thing is we cannot deploy superconductors for a long distance. For few meters definitely we can do, but superconductors, they are very expensive, and maintaining their environment isolation and all is like too difficult. So we definitely are looking at optic as a communication network. So if we have to translate from a superconducting transmon qubit to an optic qubit, obviously we need components that would be able to translate, take in the qubit output, be able to establish something called as an entanglement. We'll come to that in a few moments. We'll come to that part as well. So once we are able to do that, then we are establishing a network. So one of the easiest way to realize an end node without having to have very elaborate communication component is to deploy NV center qubit. Yesterday we spoke about NV center qubit, which can operate at standard data center condition. I mean the normal temperatures, and we can have slightly less isolation for the NV center. Obviously, you need to have a good clean room kind of a setup, but that's about it. NV center is fairly stable. And the beautiful part about NV center was that apart from qubit compute per se, it was also had the ability to shoot off electrons to the photons to the next qubit, which could be an NV center. Uh, that's fairly simple, because you now have the qubit core, which is itself is able to transmit photons. When we are able to do this setup, we generally would prefer an NV center qubit for quantum network, which is a very logical thing to do. But again, it comes with its own challenges. We spoke about it as well yesterday. About 1% of the carbon atoms we see is also C13. So we need a very extreme level of production fineness to ensure that they do not interfere so easily. So those are some of the challenges. But having said that, NV Center is more practical to be able to use in a quantum network. So we have talked about all this, and we have even seen that photons is much more reliable to be able to transport. So from a communication perspective, we are able to do that. In fact, there has been a reliable quantum teleportation that has been achieved with single photon itself across a few meters. So we are talking about teleportation. If we are having a quantum teleportation itself, then we are essentially saying that it could be replicated. If we are able to do it across few meters, we might be able to repeat that, and we might be able to build a network which is few meters apart, and we can do it across a lab. Even establishing anything beyond a couple of meters is actually an achievement with quantum computers, because that's fairly susceptible to errors from external interference and all. So actually, that's a fairly good achievement. We have also seen magnetic fields and lasers being used to drive ion traps. We spoke about ion traps as a non-solid state qubit yesterday, and this can be used to demonstrate a quantum network where you could be using magnetic fields to also transfer or also build up an entanglement. And when you are able to do that, and then obviously you are looking at in concept a communication or transportation of data. That's exactly we are trying to achieve. And we have been speaking about optic fibers as a media for transmission, but in optics, we also have an option of free space, as in you can simply in the line of sight, you have two, let's say, two different buildings, and you can, if there is no real obstruction, you can actually use in line of sight, you can simply use the free space to transmit laser based photon. You can definitely do it, but it's obviously very vulnerable to external interference. It requires uninterrupted line of sight. It requires that there are no there are no major external disturbances per se, and also you do not have large even tree leaves can simply disrupt. If it flies in the path of photon, then obviously it's going to disrupt. So those are some of the practical issues that we face with the free space. But if you look at the free space communication outside the Earth's atmosphere, which is essentially in space, then that's fairly doable. I mean, you can look at a free space quantum communication in space. Of course, you need that to be behind some planet or something, so that you are you're not interfered by a sun or such solar body. And the beauty of those kind of network is that it definitely has got a higher transmission rate. Your optic fiber generally have you will have to account for the polarization issues and the losses that accompany with optical fibers. So those kind of things do not occur here at that levels with free space transmission, and that's why we know that free space transmission typically can support higher transmission rates. But having said that, it has its own challenges, and it's not practically feasible in all the scenarios. Whereas in optical fiber communication, that's very much practical, and it's deployable in most of the scenarios. And as with a standard optic fiber, it can operate on a single mode or a multi-mode, and multi-mode obviously gives more precise communication. And we can pair it up with an avalanche photo detector at the receiver end, and we can actually set up a proper quantum communication. Uh, and typical phase and polarization controls we have been using for our regular optical communication. We have been using it. So interferometers and beam splitters can be used for quantum photon transfers, and we can simply drop in these components and in place of the existing components, and we could then leverage. The existing telecom fiber obviously can be also be kind of multiplexed to send non-quantum data, like you want to send control signal, because obviously there is going to be certain control signals that you are going to say, hey, I'm going to begin my quantum communication. So you would want to send that data first, and you might want to give some timing information, like what are the timing signals that I'm sending, what is my expected duration, and so on and so forth. So those kind of control data can be set, but at no point you can actually send quantum communication with the classical traffic. So that's how it can be leveraged. The Of all these things, we have been speaking about long distance communication, and in classical long distance communication we have a very important component, which is a repeater. So repeater, if you are talking about coax, we have standard amplifiers that can boost the signal. In case of optics, we have optical repeaters, but in quantum we cannot have an amplifier like that, because you cannot copy the qubit. So to really implement an amplifier, we if we have to look at, in theory, what we need to do is we need to capture the qubit, and which means that we should be a receiver, and we are able to do that. And we would need to understand the complete state of it, which is, again, from a quantum physics perspective, it's not doable unless you are the one who's receiving, and you're entangling the quantum. You cannot really simply re-establish the complete state as is. So for this, there is a solution which is called as either a trusted repeater or a quantum repeater. A trusted repeater is purely applicable only in the case of QKD, because out there are two bases. One basis is that we assume that the repeater is trusted, which means in the network that equipment is expected to be there, and the other party, let's say Bob and Alice, which are a classical cryptography, what you can say, actors. Okay, so between them they do a communication, and that's how we generally explain in an example. So let's say Bob and Alice are using a repeater in between. Now for Bob, the other party is no longer Alice, and it's actually the repeater. And for Alice, it's the same. So the trusted repeater becomes the other party, which it actually internally decrypts and re-encrypts the data, and using QKD, it's actually sent to the other party. So this is applicable only in the case of QKD, and this cannot be done for other use cases. So for other use cases, you need something called as a true quantum repeater. Sorry. So what you have in case of true quantum repeater is that it lets you end-to-end generation of quantum entanglement. and thereby using quantum teleportation, you are able to establish qubit transmission. So when we are talking about quantum teleportation, obviously we know that it's not something that uh, you can establish at very long distances. Obviously, for we have certain limitations in terms of how long a quantum photon can travel, and the basis of that we need to place the repeaters. But the beauty of this is that. This repeater can be done in multiple. I mean, as in you can keep repeating them because it's a repeater, so you can keep repeating them, and you can even test them using quantum key distribution protocols, because they can easily adapt to these things, and you can test that the whole quantum teleportation and the repeater, the true quantum repeater, is actually being able to help, and it's having a high fidelity, and we could do that. And in this particular case, we do not have a concept called as trusted repeater. So we do not have a concept where, so in a trusted repeater, if I have to slightly elaborate on a trusted repeater, so the trusted repeater has got a key. uh, so in a trusted repeater, when we say it has got the key, means it's able to decrypt the payload, and it's able to re-encrypt the payload. Whereas in case of quantum teleportation and quantum entanglement, when we are talking about, there is no concept of decrypting and re-encrypting the payload. Rather, you will find that the entanglement and the repeating part of the communication is actually within the quantum state itself. I mean, the quantum teleportation is which means that your quantum photon itself is being acted upon. So the data itself is being acted upon. It's not the a key which is acting, but it's actually on the payload itself. So that's how the quantum repeaters work. And if we have to do that, we do not have to actually physically send it. I mean, if you have to talk about sending the entire data of stream of qubits, we do not do that in that way. We rather do it in a way that we require a precise modeling of the quantum computing as a whole, in which we consider that there is a repeater within the network, and we know that the network is existing in this topology that we know, and basis of that we model it in a way that we are able to transmit the initial photon, and we'll come to that. And the systems which are suitable are not just end nodes. I mean, as in the quantum nodes, quantum computers alone cannot be the end nodes. Even the repeaters, without the capability of quantum gates, can also act as a repeater. I mean, you do not necessarily require an entire gate setup for a node to act as a repeater. You do not really need that. You just need that the repeater function is enabled out there, and then you are all good. So how do they really work? Let's take a case of a single repeater. We'll not talk in complex terms, because when you are talking about complex terms, you are essentially talking about an initial phase which is hopping across multiple repeaters, and you are initializing all of them, so on and so forth. So in the initialization phase, what let's assume there are two pairs of entangled bits. On the sender side, let's call it as A, and the receiver side as B, and R being the repeater. Now the repeater has got the where it have an entangled qubit for sender, so we can call that RA, and for the receiver we have an entangled qubit at the repeater, which is we can call it as RB. Now you have an RA and RA as a pair, you have B and RB as another pair. Okay. Now we create initially entangled qubits. First time we established this, and once we are done with this, we can send a qubit from A to B. And when we are sending a qubit from A to B, what we can essentially do is between RA and RB. Now, both qubits are existing in the repeater itself. So obviously they are in the same substrate. And if we are having, or as in the same base, and when we are having it in the same base, we are having two different qubits in the same base. Now what we do is internal we have an interconnect between them, and internally we can do a bell measurement within that node. And doing a bell measurement within that node is fairly straightforward. It's an established setup. So you simply do a bell measurement, and when we're doing that, we are essentially, what we are doing is, now we are translating the qubit state from RA to RB, which means we have transferred it from the sender side to the receiver side. Now, this swapping actually ensures now that since the R, B, and B are already entangled state, now what happens is, when we are having a state change in RB, obviously your B is also going to have the effect of state change. Now, once you are having established that, now essentially we are having now is A and B are now entangled, which is now we are saying that the distance between A and R, and R and B. So now, for this entire distance of both the distances taken together, now you have an entanglement of A and B. Now, if you have this, essentially we have established a quantum network between A and B. This can simply be repeated. Now, if you assume that B to be a repeater again, so instead of R, we can take X. Now, then it becomes, now it is A and X. Now, you repeat it for, let's say, for, C, which is which is a receiver. Now, if that is the case, you are essentially building a set of repeaters, and it can simply be extended. So it can be extended in a linear way. The other approach is to establish it in a hierarchical way. And uh, and I think it was again China or probably Germany. I'm not too sure. Researchers at one of the universities in either China or Germany, they had actually established a hierarchical fashion, and they had established the entanglement for a long distance. And this kind of is very important for us, because now what you are essentially doing is, you are now building a network between two qubits which are far apart. Which, when we are saying they are far apart, at the moment we are talking about a few meters or a few kilometers, uh, or it could be any distance. So we are essentially now able to set up a whole distributed computing. We'll come to that piece a little later. That gives a basis of giving a distributed computing. In fact, if we remember, this is one of the early stages of network computing, when DARPA kind of initially wanted to build a network. Essentially, they were trying to do something where they were able to have those the nodes in between that could act. I mean, in generic terms, that when they spoke about, they said, "Oh, if I could have two different computers, and if I have a repeater which is not as intelligent as our end system, but there is a certain node in between, then we must be able to ensure that we are able to transfer the data from one computer to another." And if that is the case, we are essentially building a network, and we are having two smart computing nodes at faraway distances, and we are having a less smart node. I mean, it's not like a completely dumb node. It's not simply just translating or transmitting the data. It's also doing certain certain function by itself. in a quantum repeater, it's the Bell measurement. So there is certain level of complexity involved out here, and then it's able to establish the entanglement, and via entanglement we are establishing the communication. uh, so a very curious thing usually comes up with people is that if I have this kind of communication, there are bound to be error corrections, right? So there are bound to be errors which will fall into two broad categories. With classical communication also, we do have two broad categories of errors. One is at the operation level, where you have the equipment that has got its own issues, and it introduces a lot of errors. In today's case, obviously these equipments are extremely well fine tuned, so obviously the scope for errors in a classical communication is very low. So obviously the error correction rarely occurs out there. But for communication itself, in the media we have loss. So errors do occur in those laws, in the media, and that needs to be corrected. So that's a commonality between them. But the difference between the quantum communication and the classical communication is where the parity bits or redundancies that help a classical communication. We do not have such a concept in quantum because of the no cloning theorem. We cannot have redundancy. So, what the common approach here is to distribute the quantum data across multiple entangled qubits, so that you're not having a redundancy, simply sending the same data across. But what you are doing is you are distributing the data across multiple qubits. So the operation error. So you can determine if you are having certain errors. So there are certain error detection that could be done, because if there is a loss, so obviously the end state can detect that there is a loss, but it cannot determine, it cannot recover, and it cannot simply copy a quantum state. So what it can do is it can switch to the alternate link and start communicating from the alternate link. So that's about a typical quantum communication, but we have to have a special mention for quantum key distribution here. So quantum key distribution, uh, since they are carrying classical data, right? If we detect an error, we can apply certain classical error correction methods, but again, we cannot use classical error correction for the media, because the media now is we are now using a quantum communication for it. So obviously the setup really requires a different approach, but at operational level we can compensate for the errors using classical approaches. So we spoke about all this. Then we spoke about. We had a brief mention about entanglement purification. Now, when we are transmitting, typically we spoke that there could be. We could lose certain level of coherence over a distance. So that can really occur, and qubit from a maximally entangled Bell state, um, when they are getting transmitted. Um, so uh, so that in that case, decoherence can occur. And if we are having such a scenario, what we can do is we can do an entanglement purification. Now it creates we could have certain weakly entangled qubits, and we can put them together, and we can create a nearly maximally entangled qubit from them. But that's while that has been established in NV centers, and it's of significance in long distance communication in a noisy environments. We can think of certain specialized setups where we typically are doing it right now. We can completely skip it because we do not really require that kind of consideration of errors in some of the lab with an intra lab and an inter lab kind of a setup where it's not a very long distance. We can simply skip this. But from a very long distance communication where we are using the quantum photons for a significantly long distance that we are using, then obviously we need to consider this. uh, any questions till now? Okay. The one other thing I probably forgot to mention is that while all this sounds great, and there is a good level of research and progress that is happening in the quantum communication, both for QKD and non-QKD use cases. Unlike classical networking, where there is a significant amount of standardization uh, in across maybe organizations like IEEE have done a great job in standardizing those at a fairly early stage. There is no such standardization at the physical layer for quantum computing, because quantum computing, if you understand, you cannot really standardize them in a sense that you cannot have a certain standard specification and say that, hey, I'm going to use this, and irrespective of what you do in the behind, this standard can be used and you can transmit. That's not going to happen, because the quantum qubit is now going to determine what kind of equipment you apply, and what is the kind of what is the strength of the signal that you have, and basis of that you need to have a setup which is able to scale to that. So it's not really standard from that perspective. But I believe, I mean, this is my personal opinion, that over a period of time, what will happen is the companies will come back, and they will start looking at certain level of standardization for a given environment. So let's say if I am going to have an NV center as a qubit, so I could be using so and so, and I would say that, a certain level of standardization I could do. uh, but I think by and large, certain variations will exist, and maybe for another couple of decades we may not see a broad level standardization, or probably even for more time we cannot see the kind of standardization we see in the classical network. We uh, we briefly had touched upon a point of distributed computing, so that's our important point that we are going to look at. So from a quantum network and computing standpoint, we can see that it can be applied to distributed computing, and without having to use a repeater, without having to use any of those complex setups. Two labs, obviously in the same building, what they had done in Germany was they had simply an 60-meter optical fiber between two labs which are just beside each other, and they were able to communicate. They also tried, line of sight kind of an approach, but then eventually they went for the optical fiber. So in this case, this is, in fact, they claim it to be the first distributed qubit gate, which means that there was one qubit in one lab, there was another qubit in another lab, and they together formed a gate. Now, this is very interesting concept, because if we have interconnected two qubits, and we have created a gate out of it, and we are able to perform gate operation on both the qubits with absolutely minimal latency, then what we are doing is we are essentially not just doing a distributed computing from a classical computing sense, but we are also from a quantum. This is a fundamentally different approach, because it's like saying that I have one transistor here and another transistor there, but then I'm able to operate both of them at the same time, and then my gate is established. It's equivalent of saying that, which means this is a phenomenal achievement. uh, Once you are able to have gates, and now that when complex gates are being formed, and complex gates are put together to form a solution to a problem, or probably implementing an algorithm. So what what you are essentially saying is that now you can have qubits. So I have prepared, let's say I have built a 54 qubit computer in my lab, and I'm falling short by, let's say, 6 qubits. So maybe I could ask my neighboring lab, say, "Hey, I'm falling short of 6 qubits, and do you have anything that you can share with us?" So, and if they say, "Oh, no problem. I do have 10 qubits available, which I'm not using for my gates, but eventually I'll be using. But at the moment, I'm not using. So you could probably, lend the 6 qubits." So that's a very interesting use case that they have built, and which is in a sense you can think of it as little counterintuitive, but it's so beautiful that now you no longer are restricted by your net or your own quantum computer setup. I mean, your node alone, it's it need not do the computation standalone and then do a network. So it's kind of different from what we earlier spoke. Earlier we spoke that we need two fully functioning quantum computing units, and we establish a quantum communication between them. But here the quantum communication is actually building a single unit using two different nodes. So it's different in a sense, but that's exactly what they have achieved, and this is fairly recent, a few months ago. So it's fairly recent, and their theory is that now this can be extended. Now once you have established for 60 meters, I mean that's a very long distance for a quantum computer, which is essentially you're saying that it's really they are two different units. So if that's the case, the theory now is that we can extend it to create a wider network, and larger gates can be realized using qubits which are placed apart. And even the gates themselves, they could be placed differently, and all the gates can be put together in different units, and a single quantum computer can be made by using a broader network. So they have demonstrated that you can have beyond the name and normal range of quantum qubit interconnects within the same base. They have now said that now this can be extended to larger network. This is a very useful demonstration. They do have certain error issues right now. They implemented a C naught operation, so it's a fairly simple. If you recollect, C naught is a very simple. In fact, it's one of the simplest gates, um, and they have been able to do this only with about 80% fidelity. If 20% errors are around, it's still fairly high. It's not practically feasible for repeated computations, but it's a good start for a first experiment. They did not use elaborate setup of repeaters and all, so it's a beautiful thing. So they also said it's not material dependent, as in it could be used for both solid state and non-solid state qubits. At the moment they have used NV center, but they have hypothesized that it could be used for both type of materials. And with material independence coming into play, there is also a thought process which is going around. What if you have one qubit implemented in a different way, and other qubit is implemented in a different way, and you have two different units which are implemented in two different methods, but actually they come together as a single quantum computer. So if that's the case, the we are not really tied down with the concept of having a uniformity across all, and then you have all the parameters to be same. Then you need not have that kind of a duplicate setup. You can have certain variation in the setup, but yes, if you are talking about photon based qubit, then obviously you need a photon based setup out there, but there could be certain variations that people can do. So there is certain freedom definitely which is available. Since they used, I mean, these German researchers, they had used single atom, as a qubit between the two mirrors, and they sent one single photon across the optic fiber. Um, uh, uh, you know they then entangled it with different in the different modules, and they did this. They also state that the ancilla photon approach that they have used for quantum entanglement, so this can be kind of easily repeatable, in the sense that we can without establishing expensive networking, we could repeat it across nearby labs, and so a whole building can have quantum computer setups, and you still have you need not put everything into a single place, into a single large room. So you could have adjacent rooms, and you could be having gates spread across different rooms, so that way maintenance, and it becomes more practical. I mean, from a practical perspective, you cannot have one data center which is like a very huge data center and you have everything out there. Instead, what you can have is you can have smaller rooms where you can have various experiments that are being done. But when you want to run a single large experiment, you can simply modify them in a quick time, and you are now able to build them together as a single quantum computer. So these kind of practical variations are possible, because it's fairly expensive, so obviously you want to reuse them. So this is a very interesting research that has happened, and one of the things that we are talking about, these kind of setups, is that people are becoming more and more innovative, in the sense that we need to have certain level of ingenuity to be able to extract the maximum performance from each of them, and we are able to show that leverage, and investment follows the output. So R&D investments are always dependent on the kind of innovations that come out, and that's a more practical aspect of it. Industry wants to see small, quick innovations and inventions, and so that which can be taken commercially, which can actually generate certain revenue, which can then be put back into R&D. So these kind of small steps to establishing a commercially feasible computing is essential. So we could then pair it up obviously with classical computers, and then we could extend it, and we could create a quantum primacy. If we are able to establish to much larger scale, we can do it for a quantum primacy. uh, any questions here? Because the next two slides that we are going to talk about a special use case. Okay. So before I come to this, I will quickly touch upon the clocks, because I thought maybe quantum network of clock is much more relevant here, and we could talk a little bit about the quantum network of clocks, which can help much more components than quantum computer alone. Um if we recall, the quantum repeaters and the initial entanglement, and how we established the whole network. We could do a practical implementation of this quantum network of clocks, and we can propagate the clocks to, or rather, the clock ticks to all the clocks. How do we get there? So what is the foundation of accurate timekeeping? Why is it important? I mean, in a physics sense, we know that the timekeeping is so essential for various applications. I mean, it could be as simple as giving a clock to a computer, or it could be as complex as being able to leverage it for measuring certain astrophysics data. So, and if you want to really build astrophysics equipments, astro equipments, you obviously need high accuracy, because cosmic rays, even if you're trying to decipher them, and if you go off by a few microseconds or a few nanoseconds, you are essentially you are hitting the age of the body that you're trying to look at by many years. So obviously that's a key challenge out there. So accurate timekeeping is essential in each of the fields, and in financial markets, I mean, things are working at nanosecond and microsecond level. So out there, accurate timekeeping is extremely important. And we will, from a scientific perspective, we always look at reducing the measurement errors. So measurement errors, in fact, are one of the most common errors in atomic clocks, because atomic clocks themselves have become super accurate, to the sense that the material itself have become fairly stable. And unlike earlier, when we had issues even with the clock stability itself, today the components like yttrium and erbium that we are using, we have we have a fairly stable atomic clock. But the measurement errors still exist. I mean, you have, at the end of the day, you have the equipments which are able to translate this into electrical signals. And when there is a certain translation that is happening into electrical signals, there are bound to be certain measurement errors. Even if it's very tiny, it's going to happen. And that is where a lot of these jitters occur. And that's why it has become difficult to determine what is an absolute clock tick. I mean, we are very close to that, but then we are still far away from it. I mean, if you it's kind of paradoxical that you say that 1 second in a billion years is what we are looking at as a accuracy, but 1 second in a billion years is also too much for certain applications. So how absolute is always a debatable question, but the compensation techniques that have been used to calibrate, have been fairly good, but we still have room for improvement, and that is exactly where the quantum network of clocks come in. Sorry. So how does it really work? We just need a quantum network and a quantum clock. I mean, we don't really require anything much more. We do not really need a quantum computer per se to do this, but it has implications for quantum computer, and it has implications for classical computing as well. So how does it really work is that it like a repeater, quantum repeater we spoke, where we are establishing quantum entanglement. We use a clock, the clock's quantum particles quantum state itself, and we propagate it to all the clocks. And when we are doing that, what happens is, if you think of each clock as an individual clock, now there are certain compensation techniques, mitigation to measurement errors. So each of them will have a certain level of corrections that are being applied to their measurements. Now when you start linking up all of them together, now in a sense, the compensation and error corrections actually get amplified, which means that they are now much more effective. And the overall clock, if we have to think of, let's say, all the GPS satellites put together. So US has got, I do not recollect, maybe 28 GPS satellites. So let's say those 28 GPS satellites are talking together, and they have this atomic clock with them. So let's say that these atomic clocks are actually entangled with each other. Now, these entanglements would actually mean that let's say, I mean, I'm just creating a hypothetical situation right now. So at the moment, they have not implemented it, but let's say they implement it. So if they are entangled, what happens now is, with the current accuracy that they are having, they will probably establish much higher. And the implication of those clock accuracy is huge, because these GPS satellites are extremely, widely used. So financial markets, and because I do understand the financial markets. So earlier, my customers used to be, they used to be large financial trading firms, and there used to be, in fact, we had one of our customer was also a stock exchange. So we know that they widely use GPS signals to time their servers. And if we are looking at timing these servers to that accuracy, then if we are having a clock at the ground, and we are having a clock in for the satellites, and if we are able to establish an entanglement like Chinese did, even from ground to satellite kind of a link. So if we are able to do all this, then essentially what you are doing is you are creating an absolutely accurate, or what we can say, to a very high degree of accuracy. It's not absolute, but to a very high degree of accuracy, you are establishing the time clocks. And that's great, because you can pair it up with NTP, you can pair it up with any of the other protocols, you can pair it up, and then you are having the whole classical network to be in sync, and the time accuracy is much better. uh, what is the implication of this in our quantum computer? The quantum computer, if you remember, for the supercomputer transmon qubits, we obviously required, the control of frequencies. And if we are having a frequency control out there, and if we are having a clock, and if we are having, the frequency controls, the timing, the measurements, we can align all of them to the quantum clock. And then we can have far more accuracy in the measurement. Today, if I have to give you an analogy, and I spoke about it yesterday also, there is this company about Q Control, where they do an analysis on the measurement errors, and on the ancillary data, which is not on the actual quantum data itself, but the ancillary data which comes out of sensors and all. um, if we can pair it up with a quantum clock, I mean, imagine the accuracy that you would get, and now you are able to pinpoint at a precise, nanosecond, particular thing happened. And if you are able to pinpoint to that level of accuracy, very tiny, variations or runaway that can happen. So those things can be captured very easily. And once you are able to have that, your tuning of your components, the parameters that you're supplying to your ADCs and DACs, now those can now be controlled in a much better way. If you are able to control those chips in a better way, we spoke about Google engineers having built a CMOS chip, which is doing this kind of a control. Now imagine that chip getting the quantum clock. Now the kind of accuracy that we are looking again is like phenomenal. So that's why we are looking at quantum clock as a major research. And still there is no commercially deployable quantum clock network which is done. But definitely there is a good amount of progress that have been done in the research, and labs, they are able to establish this. In fact, there's again the same German lab which did this the earlier research we spoke about. So they also did something called as uh, a modem. So they use this quantum clock approach. The way they have done, the MIT team had done similar approach, they had also done, and they were also able to use it to create this repeater. So if two quantum qubits they are able to do repeater with the kind of accuracy that we are seeing. So then obviously it's headed in the right direction in terms of maturity of this ecosystem. Any questions here? We can move to the other slide.
Hello, sir. Hello,
Yeah,
sir. I have a question.
sure.
You are talking about quantum entanglement, and
Correct.
my question is that the first entanglement, as I know, is given
Hmm.
by Einstein, Podolsky, and Rosen in 1935 in its
Hmm.
paper Spooky at a Distance.
Correct.
It is talking about that is two particular entanglement. Now, my point is that what is that another way of entanglement that is called GHZ state? What is the basic difference between them?
Pardon, what excited state you're talking about?
No, no. You are talking about entanglement. Then
Correct.
that is Einstein has given in 1935 that the
Correct.
concept of entanglement in its paper
Correct.
in PRL, Spooky at a Distance.
Correct.
But in 1900, I think 98,
Hmm.
the three scientists they have also given a state that is called a GHZ state. It's basically also an entanglement state. But what is the basic difference between these two entanglements?
So I'm not really, recollecting that. So maybe I could refer back with some researcher. I could connect back, and maybe I can get back to you. At the moment, I do not have an answer for that.
Okay, thank you, sir.
Yeah. But point taken. So yesterday, in fact, for a couple of questions that came up, I had shared some of my thoughts and reference links. So
Okay,
what
okay.
we could, yeah,
Sir, I have gone to that paper.
yeah, we
Actually,
will.
basically, it is doing the Hamiltonian simulation, but it is not doing the initializations of any classical information to into quantum information.
Yeah,
That paper.
we'll come to that. Yeah, we'll
Oh,
come
okay,
to that.
okay,
So,
okay,
so
okay.
also for this, so what I'm proposing is, what we will do is we will have a offline follow up, call maybe sometime at a convenient time for both of us. We could reconnect. That's not a problem. Yeah,
Okay,
we
sir.
could.
Thank you.
We'll share our research notes, and we can definitely do this.
No,
Yeah,
no, sir. Your call is recorded. We can also follow it again if you have
yeah,
any doubt.
sure.
Sure.
Okay. So if we will have to go back to the previous slide, and this is one of my areas of interest, and which is I mean, right from my classical computing days, when I started, for me, security and encryption had been one of my key areas, and I had been instrumental in implementing highly secure payment networks, and I've been involved in doing the VAPT of or rather facilitating the VAPT of our applications at the banks. So I've been doing all that. So for me, when this whole journey of QKD and quantum computers and the security scene actually started, it kind of spooked me, and I'll tell you why it spooked me, um, because now it has got a phenomenal computing power. We really know that what are the capabilities of a quantum computer. So one of the scenarios, and this is I'm taking from NIST US, and this particular scenario has been extensively discussed in the last two conferences they had internally, where they had various experts contribute to their knowledge base on this. One of the major problems is that you could have a harvest and crack decrypt attack, and this is something that everybody is worried about, and very very much valid. Now, I'm going to give you an analogy. We all have been using internet banking, and some of the, or rather, a lot of banks actually do not ask you to reset your password every 3 months or 6 months. Maybe HDFC does. ICICI Bank has not been doing this for a long time. I mean, they have, at least for one of my father's account, they haven't really been asking to reset the password for like uh, 10 years now. So they haven't really asked me to do that. Imagine if whereas the whole encryption, data at rest, everything has been taken care of, and they have been encrypting the data. uh, what if, let's say, I walk into their data center, I somehow figure a way out to get hold of the disk which is holding the database, and I walk away with the disk, and now I have this whole database. I have this whole database which is holding all the users' credentials, right? And I walk away with it. Now, I know that for a fact that because it's highly encrypted, I cannot easily crack the key. And even if I deploy a supercomputer, it's going to take me like many months before I can get crack the key in a brute way. So the brute force approach is the most practical or impractical, depending upon how you look at it. But other approaches are not very reliable. I mean, brute force is the only reliable way when it comes to cracking today's strong encryption keys. Okay, so imagine this scenario. I'm having this, and 2 years later, I know that I have this data. All that I have to do is maybe just simply stream this data from my classical computer and to my quantum computer, and start seeing if I can crack this data using quantum computer. The beauty here is I could technically do it. I mean, today's 54 qubit cannot do it, but if we have a 1000 qubit digital gate qubit computer, and if I have such a setup, I could easily do it in a matter of seconds. If I'm able to do it, once I have that key, now all that I do is go back to my hard drive. I use the key, and in a matter of couple of hours, I'm able to decrypt the whole disk. My entire hard disk is now decrypted. Once my hard disk is decrypted, all that I have to do is attach the database to the correct environment. I supply the password, and I simply pull the data out. As simple as that. Now I have essentially, in theory, I could have access to all the bank's bank username and passwords. That's really scary, because people don't usually change their bank password for a long time. They don't like to. And even if I am storing the data now and 2 years later I know for a fact that nearly 80-90% of the users would not have changed their password. And if that's the case, that's very scary, right? And if the database also contains how much money they have in the bank, I know precisely which account to target. I mean, it becomes scarier than that when we are talking about even bigger security threats. And walking into a data center and just walking away with the disk is not really easy, and it's way too difficult. We are not Hollywood movies where we like Mission Impossible, we just go in and walk away with the disk. We cannot really do that. What in a technical sense, what we can do is, and which is feasible even today, is that you have something called as multi-port network cards, and most of the data centers employ servers with multi-port network cards. And these network cards, what you can essentially do is you have 2 LAN cables or 4 LAN cables going into the same network card, and they are sitting inside a single server. So a single server having connecting to 4 different networks essentially. And that is what usually done for a DMZ server. I mean, you connect them to 2 different networks, and DMZ is established. And you have traffic coming from both of these, and your application can listen on to a particular traffic, or your application can listen to on a port for both the network cables. And now what happens is you could, in theory, if you have access to the server, classical server, you could simply go there. You could turn on certain flags in the driver, and you could establish something called as a traffic mirroring mode. And you can do it even in cloud. I mean, if you look at Google Cloud or an Amazon Cloud, you have click and deploy kind of a mechanism for enabling traffic mirroring. So essentially what happens in that mode is you are able to replicate the traffic which is running on one cable. You are able to move it to another cable as packets. You simply transfer the packets. Now, what I could do is on the other end of this cable, I could essentially be having a receiving device which could simply record all the traffic and do nothing about it. Simply keep recording. And I could be a legitimate user for that receiving device, because no provider is going to ask me what I'm doing with my device. Okay, they do not obviously want to allow you to tinker with somebody else's, but if you have done it, and if nobody has found out, it's fairly simple. But what happens in a classical network, classical quantum network is that, sorry, a classical network is that your traffic is also monitored. So there is certain pattern that you can establish, and people will figure out that there is something wrong out here. Imagine if I am establishing a QKD network. In a QKD network, what we are saying is that it's tamper proof. I mean, in the sense that you cannot really even figure out what traffic is going on. So there is no way that anybody can prove that the QKD network is doing anything harmful. For all that, it might be that you might be offering a service, and you are establishing a QKD network with one of the bank's database servers, and you are having, and you are in fact what you are doing is you are pulling all the data through the QKD network, and you are recording it in your classical computer, and you are that's a harvest that you are doing right now. And this is exactly the practical possibility that can happen. While there are certain practical challenges in terms of how you establish them, that's a different story. But once you establish them, then there is no way that anybody can stop you. Legally, nobody can stop you, and that becomes a major headache. And this is exactly what the Mosca theorem is, where if they say that if my secret key have a longevity, and if my data have got a longevity more than my time, that in which a strong quantum computer can be established, then obviously then we need to worry, because now we would be able to do that harvest and decrypt attack, and it becomes much more important for national level security issues. So that's why this is of a great concern right now. So what do you do out there? I mean, technically, if this is established, you can do nothing. You can really do nothing legally, because you cannot prove that it's carrying a harmful data. By no means you can do it. And the person who is receiving it, without coercion, you cannot ask them to give up what data they have. So obviously that's not going to happen. So it's too difficult for such a scenario to exist, and that is why this is a practical problem that needs to be addressed. So yeah, certain process can be enforced and certain things can be done, but eventually we know that at the end of the day, if somebody is snooping my network, I mean, forget about being on my computer. If they are doing tapping man in the middle kind of an attack, it can still cause troubles for me, because now that I'm or simply eavesdropping at a classical repeater, right? And they are able to establish a repeater which is splitting the data, which is not just replicating the data at a repeater level. There is no way anybody can do it. I mean, data center, at least you will know that somebody has gone and plugged in a cable to another server. But if you are doing it at a network level, there is no way that you can establish what has gone wrong. So these are some of the practical scenarios that exist. In the long run, we would definitely need to evolve certain defense, and that is where companies like UNU Labs and a couple of them in US have really come up with some innovative approaches to it. But again, we are still a long way ahead in terms of solving this problem. And Where does a quantum computer sit in all this? It can be used for a malicious purpose. And once, I mean, it's not going to be very far away when a quantum computer is going to be used for a malicious purpose, because as long as it is within the labs, within universities, we know for a fact that in a greater sense, it's not generally used for a malicious purpose, but it could be if it's driven by the government itself, if they have programs to do such certain things, then obviously it's going to be. But when it becomes commercial, when quantum computing becomes commercial, and commercially, when you start getting these things, at the moment you do not have access to the entire computing power of IBM or Google or Amazon's. Quantum computing, which is still in more of a research kind of a situation. You do not have a large capability available. But once you start getting those, once you start getting them as cloud service, it's going to be phenomenally difficult, and that is where there are concerns, and we probably have about 5 to 10 years max before such scenarios begin to happen. So research is going on in this field, and this is one of the my favorite research topic. In fact, on the security. To me, I'm in fact discussing with a few folks to see if there are any new concepts which are coming around. At the moment, there is a very few research that are being done here, and this is one great area of interest. Um, the other factor here is that quantum computer, when we talk about quantum computing hardware per se, the beauty of it is once you do, since it's a co-processor, it does not have its own storage by itself. We do have concepts of quantum memory, but that is not expendable, or that's not expandable for long-term storage, and it's rather expendable in the sense that you could simply have it for a shorter usage for a quantum repeater kind of a scenario, but you do not have a long-term storage. And that's where the worry is, because now once the compute is done, like a microprocessor, classical microprocessor, the trace of any compute is gone. I mean, it doesn't have any trace of what computation has been done. So that's another challenge. You do not have a mechanism to copy what has been done. A classical computer, you can at least enforce certain audit logs. The concept of audit logs in a classical computing is that whatever action that happens at a fairly low level can also be audited, which is not the case with a quantum computer, except for the sensor data, which is classical data, external measurement, equipments, or the instrumentation that we have. That operates on the classical data, but the quantum computer itself will not give you out what operation has been done. So there is no way to figure out what operation has been done. There is no footprint of what was done. So that's a major concern. And that is where there is also research about how do we build a system which is also able to enforce those kind of mechanisms. So that's a long research, that's a long path ahead, and we are kind of in a very fairly initial stage in that. So that's about security, and that's about QKD, the quantum networks that we have been talking at a fairly high level. We could definitely have a detailed, discussion about the papers. I have no more slides, and I'm kind of having a short discussion, because I believe this is a good start, and I am throwing the floor open for any questions.
So I request the participants to raise some queries. If they have some queries, please raise.
Okay. Since there are no immediate queries, we could definitely connect at a leisure time. Both your time and mine are kind of hardbound at 11. So what I'm going to do is I'm going to quickly put across a couple of questions for the audience. Is there any specific field that each of you are interested in? I mean, I understand that. Some of you have been exploring quantum computing for a while, and some of you are new to it. So is there any specific area that you are interested in? Okay.
Sir, I am interested in that quantum machine learning, and I saw that they are giving, but really no quantum machine learning concept is discussing here.
Oh yes, absolutely. Quantum machine learning. In fact, in one of my previous sessions in one of the universities, we had a long 3 hour session for, I mean, similarly one and a half kind of a session on quantum machine learning. So what I could give you a brief about quantum machine learning. In fact, I'm not sure if I have that slide right now. Let me just give me a moment, and I will give you a certain background to it. And quantum machine learning is also, I mean, in a way, it is also related to your quantum hardware, because there's a beautiful dependency. Let me just quickly bring this up. Okay, so quantum machine learning it's actually is a very interesting field, and there is a lot of work which are going on. Out here, let's assume, and I'm going to give a quick 10-minute walkthrough, and I'm going to tell you how it also relates to the quantum hardware. Let's say in a bank we have millions of fund transfer accounts, and you have a typical transaction usually has about 100 to 200 odd, or sometimes even 400 odd fields. So what we do is we call them features for the parlance of machine learning. So in machine learning, how do you identify a pattern of fraud in so many fields across so many records, millions of records? So a classical problem, or a classical rule approach, logic Java code cannot really solve this problem. You cannot identify the pattern so easily. And the other thing is, how do we stop the fraud? I mean, your transaction happens in under a few seconds, right? It doesn't, when you do a fund transfer, you are completing the whole process in, like, let's say, less than a minute or 2 minutes. You don't really take much more time, and we are talking about end-to-end transaction, and the actual transaction in flight is like a few seconds. So how do you identify a potential fraud in that? So that is where machine learning comes in, and machine learning is typically consists of supervised, unsupervised, semi-supervised, and reinforcement learning. And banks typically employ supervised learning, and they because it's much more comfortable for them. And unsupervised, you only do clustering, and you do not have the concept of labeling. Whereas in a supervised, you are able to label each transaction as a genuine or a fraud transaction. As in a practical example, typically when a transaction happens, you by default you flag it as a genuine, and if you find a pattern which is not genuine, then you apply a non-genuine pattern to it, or a flag or a label to it. In machine learning terms, we call it a labeling. And once that label is done, when you want to retrain the data on the new transactions, so what happens is all the new labels are also taken into account. And if some customer calls up and says, hey, this is my fraud transaction, so the first thing they do is go and label it as a fraud transaction or a potential fraud transaction, so that the next time the machine learning runs, it tries to take that into account. And semi-supervised is somewhere in between your unsupervised and supervised learning. It's not, again, there are limited use cases for it, but it's more practical when the labeling is very expensive. but that's a different use case. But so practically we see that supervised or a semi-supervised is what a lot of companies are employing. Reinforcement is usually used in in specialized cases like automated autonomous cars, like Tesla's autopilot, right? It uses reinforcement in the background. So they have a very, very large data center in California where they are running this whole reinforcement, and that is then that the whole trained model is given back to the Tesla car, and it's able to infer at runtime, and it's able to take certain decisions by itself. So that's what they are. And machine learning, I'm going to quickly walk through what are the typical ones. Supervised cases like housing price or medical imaging, where you have to do a classification or a regression. In unsupervised, you usually do it for marketing, or more of a basket kind of analysis where you have a clustering, you have an association. So these are used usually in retail industries or in financial markets where you want to assess a basket of stocks. Let's say all the pharma company stocks you want to analyze. So you typically will run a unsupervised ML on this. And semi-supervised text classification, one of the projects that I had executed. And the clustering, again, lane finding on the GPS data. This is, you will see Google Maps using clustering in the background for showing you, if you zoom in enough, it will show you take the flyover, or you go below the flyover. So those kind of lane finding, and specifically lane level traffic. So those things are, in the background, what it runs is a semi-supervised in conjunction with a classical Java code. So that's what they do. In reinforcement, we spoke about autonomous cars, and again, classification, some optimized marketing, similar to customer segmentation, but it runs optimization problems out here, and it is a classification. When I implemented a text classification, I'm not getting into detail of this, but it was more like leveraging Levenson distance, which is a common non-ML logic, but it's more of a statistical logic, and combined with classification, text classification logic. We combined both of them, and we had a good outcome. We had an outcome of about 90 to 95% confidence level. That's fairly good for that kind of a use case. We had a very complex use case where we had to map different descriptions of hotel rooms into categories of hotels. So categories, you had to label them autonomously. So that was more of text classification problem we had solved. Now, moving on to the deep learning. Deep learning is where quantum computing can actually help out here. We have, in classical sense, we have convolutional neural networks, recurrent neural networks, self-organized maps, and autoencoders. We talk only about the supervised, and in supervised we have a CNN or an RNN. When you are implementing a quantum hardware for a CNN or an RNN, you are essentially doing something called as a QNN. So if you look at specifically on the QNN research papers, you will find there's a large progress that has been made on QNN. There are certain challenges. We'll come to that. We have a lot of standard ML frameworks and libraries like TensorFlow, Keras, PyTorch, and Theano. And TensorFlow, in fact, came up with quantum computing add-on, and which is now getting integrated. So you have a quantum TensorFlow specifically where you can leverage quantum machine learning. And underneath, it will be able to identify what is the kind of computing power that you have, and why is quantum machine learning needed. So obviously we have spoken about the optimization problems and the decisioning problems which are NP hard, and optimization problems. We saw that quantum annealing can help you solve some of the optimization problems like D-Wave. While there are certain people who say that okay, quantum annealing is not as powerful as what it is made out to be, my opinion is that quantum annealing definitely has got certain advantage over classical supercomputers or a classical large computation or a deep learning, in the sense that it's able to do it much better. Okay, it's able to do it in a sense that it's not just doing a heuristic approach. It can also take a pure solving approach, and hence we need quantum machine learning. And in deep learning, there are specific use cases where the optimization weights of neurons in multi-layer network. So if I may just step back a couple of steps, out here you see there are so many repeated nodes. So the green ones are the delimiters, if you can think of, and if you see that those are that's a particular node doing a set of operations. Now each of them we will have to, in a resonate, we have to apply certain weights, and there are certain ways in which it is optimized. But in an unoptimized deep neural network, deep learning neural network, each node you have to assign weights. Assigning weight itself becomes a kind of a NP hard problem in an absolute sense. Again, out there you have to apply heuristic, so it becomes much more complex. I mean, you are not able to leverage the 100% capability of deep learning then. So quantum annealing can be applied to optimizing weights of the neuron in deep learning, and then you can give it to a deep learning, and deep learning can actually do its job. So that way we can leverage quantum computing, and we have already spoken about security threats. So there are different things that we are looking at when we are saying quantum machine learning. So quantum computing can be made more accurate. We've spoken about this, where Q control toolkit can be used to analyze the control data, and this is where quantum machine learning comes in. I mean, in the sense that you can apply classical machine learning to the control data and feed it back to the quantum control units, which can in turn improve the quantum efficiency. And the other is the ML efficiency, where we already spoke, assigning the weights and all. There is another approach where we have the core of the core computing unit itself can be a quantum computing. So it could be a quantum computing node, and we have different nodes. So here the quantum network can be leveraged, and quantum network can be leveraged, or a classical network with a quantum node in a standalone mode, so that also can be leveraged. So this is where you can actually, so this is a practical application of a quantum computer, a quantum network, and a classical machine learning. You put them together and you would be able to solve some of the most intensive computations that you can find. So that's exactly where they meet, and the approaches that typically the industry takes is that you at the moment the quantum computing is fairly in a nascent stage, so they kind of keep it as a standalone, but eventually what will happen is they will mesh together into one, but at the moment they are kind of standalone. So that's a current status. Industry at any point of time, I believe, this is my personal opinion, is that they will go for an auxiliary approach better, in the sense that they will not have a quantum network to establish a quantum machine learning, for a simple reason. Your quantum network itself is a specialized setup, so you are tying down to one particular what I can say implementation. Unless a generic quantum network implementation arrives, at the moment the industry would view it as a specialized installation, and obviously then industry doesn't really prefer that. So that's exactly where we are looking at. And let me skip this, and So let me skip this. So I'll come to this. So important part here is you have classical neural networks which can interact with the quantum nodes, and eventually together they give one output. So March 2020, Google releases TensorFlow Quantum, which kind of abstracts all these complexities. So it's actually where quantum computing is a step within a classification system. Is one of the examples that they have mentioned that can be leveraged. So somebody who can explore TensorFlow Quantum would find that there are specific use cases that are readily implementable using them. But
so excuse me, sir.
sure.
In your side, as you have shown, that there is also that your TensorFlow, quantum TensorFlow, and also your GUIST. They're implementing in their software. They have implemented a kind of a classification, a kind of algorithm that is called quantum variational classifier. Actually, I'm not sure in which class this quantum variational classifier is going. Either it is a supervised, unsupervised,
no,
or
it's an
reinforcement.
unsupervised. It's an unsupervised one. So, or it could be a semi-supervised, depending upon if there are any labeling available. So, whenever you are talking about classification is a unsupervised. But if there is some labeling available in the
no, they are not mentioning any classification. They are saying that quantum variational approach, but they are not saying that classification or cost.
Okay, then I will have to refer that. I will get back to you on that.
Okay.
Yeah. So that's the approach that we are talking about. So the quantum machine learning is still slightly, what I can say, slightly more mature than what people think. I mean, there is now that you have a library which is available where people are able to implement, and people are able to realize how it comes through, right? So when you start seeing then output, then people start getting ideas about how to wrap it. So now people are thinking how to wrap TensorFlow Quantum and expose it as a single application. So those kind of ideas are going through. So it's not very far before we start seeing some commercial implementation, maybe a year or 2 years before we start certain commercial implementations here. And if I will have to get into a little more details as how you can look at equivalence. So you can for things like Bayesian theory or hidden Markov models, for a quantum system we need to actually need to completely rewrite or completely re-implement. But if you're looking at k nearest neighbor or clustering or support vector machines, which are unsupervised methods in machine learning, we could we could simply apply quantum computing to it. I mean, it's as simple as dropping in for that particular computation and get the output, and then give it back to the machine learning as a classical data. So that's one of the things. And for neural networks and decision trees, we need a gate approach because you cannot implement it directly, or quantum annealing cannot directly work. Even analog quantum computers cannot be done. So you need to take a gate approach, and you need to establish gates, and you need to establish a quantum network here as an equivalent of a neural network across multiple nodes. You have to establish quantum networks across the nodes, or if you want to have the maximum efficiency from it, you establish a quantum network, and then you supply the whole problem statement to it, and then get the output, and then combine it with the classical machine learning, or combine it with classical logic, and then give the output. So that's exactly what people are doing right now. I mean, all of this are in research, so there is no solid implementation which is repeatable, or what we can say is commercially usable, even for a POC purpose, right? It's not really usable. But yeah, the research is in a fairly good stage. Any other questions? Okay. I saw one from Dr. Rajesh, scope of quantum computing in VLSI. So if you look at VLSI, I think these are complementary in the sense that um, you need as I explained yesterday, right? You could be needing processors which would complement quantum computing, quantum hardware here, and quantum hardware, I mean, semiconductor quantum dots can be, in a sense, be thought of as a VLSI implementation. I mean, you could create chips out of semiconductor quantum dots. It's the as we discussed yesterday, right? The quantum semiconductor quantum dot preparation is not very different from your current chip manufacturing process. The same lithography and all, but with minor variations, which is easily doable in a assembly line. So in VLSI, we can say that one of the approaches is easy, but implementing a superconducting transmon or a NV center, diamond NV center is way too difficult at VLSI. You cannot really embed them within a chip. It's too difficult, and also you cannot service them because they are not truly what I can say. In a chip parlance, we do this stress test, and we do this. We apply. We see if it's fall jerks. So a lot of these physical endurance tests that we run, so that a typical NV center or at superconductor transmon cannot take. Those kind of interferences are very difficult for them to take. So there are limited use cases that we can see in VLSI when we are directly embedding quantum computing there. But since the research is already going on, probably we might see some efficient semiconductor quantum dots available, and photonics is one brilliant use case which is applicable for VLSI, because people are able to put photonics into a chip. When we are able to put photonics into a chip, and you are able to do quantum computing with it, then you are essentially putting quantum computing into a chip. And so that's exactly what we can do. Then other question is quantum image processing. Well, I would have to understand what progress has been made in this area, because to the last extent that I remember, image processing is extremely well established using classical computers. You don't really, it doesn't fall under the category of an NP hard problem. So quantum computers are in the current state, and probably in a foreseeable future, we see that as more of a co-processor for NP hard problems, or problems where we are applying heuristics, and we are applying other optimization techniques, and we are not directly solving them. So I do not see image processing to be used, while some research have been done in it, but I do not see a practical application of it right now. And the other factor is that if you are combining, let's say, an astro data with image processing, I might as well say that your astro data could, in a raw form, could be fed into a quantum computer to solve some of the problems, and the data taken out, and then in a classical computer you could combine it with the image processing, and you can arrive at an output. So that's exactly where we are. So if there are any specific problems, I mean, if you are looking at even extreme video processing or extreme, very large image processing where you are having billions of pixels, so on and so forth. So even out there, a GPU grid would solve your problem in a matter of minutes, and we would rather take a GPU approach where you have an array of GPUs, NVIDIA Titan GPUs, or that kind of high-end GPUs you can put, which is more cost-effective and much more efficient than a quantum computer today. And I believe that should solve your problem. Any follow-up questions on these? Okay. Okay, I believe there are no further questions. So I can be reached at this email ID. So if you have anybody has got any questions, feel free to shoot it out. Or if you have any thought process on any of the research, and probably you have any specific ideas, definitely I can help you with whatever inputs or materials that I have.
Okay, so if there is no further queries from the participant side, then we are going to close this session. We thank our resource person, Mr. Carthic Kameswaran, for having two nice sessions in this FDP. We are really thankful to him.
Thanks, Mr. Manash, and thanks everyone. You have been a great audience, and looking forward to more interactions in the future. Okay.
Yeah.
Thanks everyone.
Okay, thank you very much.
Thank you, sir.